from University of Wisconsin, and he will speak about from Boltzmann to Euler, Hilbert sixth problem revisit.
Thank you very much. Thanks to the organizers of the special semester here at the Dute Institute for allowing me to come and visit for the month of March. Thanks to Alexander Gorban coming all the way from Leicester and coming down for the day. And of course, since this is being put on the web, I have to thank the Simons Foundation for paying for the trip. So the topic is Boltzmann to Euler, and in fact I have two sets of slides, and the reason is, as I mentioned to some people, the last time I spoke at the Newton Institute was 2003, which is 11 years ago, and if I add 11 years to my current age, the chances of speaking again are rather small, statistically speaking. So I'll take advantage and tell you everything I know in 55 minutes. So what's the story? And of course, so there's the outline. That's not important. So here's a quick version of Hilbert's sixth problem. So Hilbert in 1900 gave his famous ICM address where he proposed a bunch of problems. And one of the problems was the problem of limiting processes which lead from the atomistic view to the laws of motion of continua. And Hilbert mentions Boltzmann by name. And he said, so a passage from the kinetic Boltzmann equation for rarefied gas to the continuum limit of the Euler equations as the Newton number goes to zero. So can we derive continuum mechanics from statistical mechanics? Of course, Hilbert proposed this, and of course he was a contemporary of Boltzmann and was living after Maxwell, so he was quite familiar with the kinetic theory of gases. And Hilbert, being a reductionist, believed that all problems could be mathematics could be derivable. True mathematics, the true statements of mathematics, could be derived from an axiomatic formulation, and the view was to axiomatize mechanics. Okay, and I put in the blue, as of this moment, success in the problem has been limited to cases where the limit problem possessed smooth solutions, that is, before shock formation. So, and an excellent up-to-date survey may be found in the Book of Law St. Ramon on when you can pass to the limit successfully. More or less, you need smooth solutions. Okay. So then I asked the rhetorical question, because I'll give an answer. Is there an inherent mathematical reason that makes Hilbert's sixth problem unattainable? And can we pinpoint this reason in a simple mathematical form? Okay, so here's the Boltzmann equation. I won't give you all the story. I assume most people here are familiar with the Boltzmann equation. It just relates the probability of finding a particle molecule of gas at a point x right there at time t moving with velocity psi through the air. Actually, the particle will be moving through a vacuum. And we allow all particle velocities minus infinity to plus infinity. And the function then can be used f can be determined to determine the macroscopic fluid variables via taking moments. That is, you multiply the Boltzmann equation by the number 1, the vector psi, the scalar psi squared, and you can derive the equations of mass, momentum, and energy. However, that still doesn't tell you the balance laws. You still have to know what f is. And one way to find out what f is, I could use the pointer, but here it is, was suggested first by Hilbert himself, who suggested a asymptotic, in fact an analytic expansion of the function f in terms of the Newton number epsilon. But Chapman and Ensgog reformulated the Hilbert expansion and viewed that f should be expanded in terms of the macroscopic variables, m standing for macroscopic. So m would be the density, rho, the momentum, rho times the vector u, u being the velocity, the macroscopic velocity of the gas, and theta denoting the temperature. So that's the Chapman-Enskog expansion. And of course, it became popularized in the book of Chapman and Cowling. So far, so good? Okay. So if you plug in and you start balancing powers of epsilon, you get F0, and that's the usual local Maxwellian, otherwise known as a Gaussian. So you have F0, the Gaussian, that depends on the macroscopic guys, rho, velocity, temperature. You plug that into the balance laws of the first five moments, which is 1 psi squared, which is 2, 1 psi, which is 3, because psi is a 3 vector, and psi squared, which is a scalar, so it gives 5 moments. And you plug in the first approximation, F0, and you get the balance laws of mass, momentum, and energy for an ideal fluid. Very nice. So it looks like Hilbert's program was looking pretty good. But of course, F0 was only an approximation to the problem. Okay, it was just the first term of the expansion. Okay, then you say, oh, the first term was good. How about going out one more term? So now you compute F1. Now, Hilbert computed F1 by writing down an integral equation. And this is one of the reasons Hilbert invented the theory of integral equations. It was to solve for the F1, and canonically then F2, F3, F4. Okay, but if you do it in the form of suggested by Chapman and Enskog, and you assume that the F1, I'll go back, depends on m and its derivatives, so space derivatives, and you plug in, okay, you plug in the next one, and what do you get? You get Navier-Stokes equations, so-called compressible Navier-Stokes. I'm sure Hilbert did this, and he must have been very happy, because he does it, first term Euler, second term Navier-Stokes, this is really looking good. Then Hilbert goes to Paris and suggests, okay, the problems. Okay, so now you'd say if order 1 or order 0 was good, and order 1 was better, then the next order, which is order epsilon squared, should be better than that. That's proof by induction. Okay. Unfortunately, no such luck. You go out to order epsilon squared, and things get worse. Okay, that was worked out by Burnett, who was published in the Journal of the London Math Society in the 1930s, something, I think 31. He was living in South Africa. And so Burnett went out to order epsilon squared. It takes pages of computation. Burnett worked it out. And you could continue past order epsilon cubed. And so what's the problem? Okay, so as I said here, the success of the Chapman-Enskog expansion to deliver the well-known Navier-Stokes theory, Fourier theory at order epsilon has motivated many to try to use it. But as we see, okay, there's a problem with just using Navier-Stokes theory. And people tend to slough over this. So for those who want something very simple, and this is nothing deep in this lecture, how about the standard problem? Everybody teaches PDE or PDE for engineers, and one problem in the books is always given by solving the shock structure problem and solving the famous Burger's equation. So there's the so-called inverted Burger's equation. Of course, it develops shocks, and the question is, how can you find out the good shock from the bad shock? And the answer is, put in epsilon uxx, and then look for traveling wave solutions. And that imitates the shape of a shock. As you take epsilon, go to 0, it looks like a step function that's moving along, which is the moving shock wave. So if you plug in and do the standard computation, you look for a solution that depends on x minus ct over epsilon. You plug it into the Burger's equation, and you get an ODE, which is very nice. Okay, so now we've gotten the ODE, and we can now solve. When you can solve for the ODE, you get a picture of the shock. But notice something that people tend to forget in the story, which is that in the process of looking for the shock wave solution from Berger's equation, the equation here for the ODE, let's see if it comes up. I push the button, do you see any red? Oh, there. There's some red someplace. Anyways, the ODE, there it is. Okay, no epsilon. Okay, so the epsilon has been scaled out, rather trivial observation. So there is no concept of small derivative. So if you're doing this Chapman-Ensgog expansion and say, oh, I like the first term, but I don't like the second term, or I like the second term and not the third term, it's nonsense. As I always say this thing, mathematicians are very reasonable people and very rational people, except when they want to get to their favorite equation. And then they'll use all sorts of nonsense to get to the story that they want anyways. Okay, I've put this in a quote, and this, Cambridge being a scholarly institution, I assume everybody is knowledgeable in Latin. And here's the quote. So first of all, I say, so the epsilon's been scaled out, hence any study of non-smooth hydrodynamics via truncation of the Chapman-Ensgog expansion, that is, say, using Navier-Stokes Fourier, while convenient. You want to do it? Do it. Okay. But don't talk about Chapman-Ensgog. And I gave the quote that in Latin it would be vacinium ex eventu, which I'm sure everybody knew, but anyways. And that comes from one of my favorite books by James Kugel, who used to be a professor at Harvard. And the translation for Latin, those of you who don't speak Latin in your everyday going around in Cambridge, is it's a pseudo-prophecy written after the event. That is, you like Navier-Stokes Fourier, and you make up a prophecy that Chapman-Ensgog would have predicted it. But that's nonsense. Chapman-Ensgog does not predict Navier-Stokes Fourier. Okay. And if you want to use Navier-Stokes Fourier, if it makes you feel good, you sleep better at night, that's fine. But it has nothing to do with Chapman-Ensgog. And hence nothing to do with Boltzmann. Okay, let's continue. Nevertheless, the Chapman-Ensgog expansion is an appealing tool since it allows us to cast Hilbert's question in the language of PDE. And I was going to make one blackboard now. So here's kinetic theory, kinetic equations. Okay, and we like to go to Euler. And if you're really good in kinetic theory of gases and PDEs, maybe you can do it. But for most normal people, it would be an easier procedure to go to kinetic equations to PDE to Euler. So the whole idea of the project is to find the PDE that represents the kinetic equations and then see if you can pass to Euler, because PDE people are much better at passing to limits than kinetic theory people. No insult to kinetic theory people, but they have fewer tools because the problem is harder. Okay, so, but if truncations of Chapman-Ensgog are illegitimate for non-smooth solutions of the fluid equations, that leaves us only one recourse. And this I learned from Alexander, which is, you can't truncate. Well, what does it mean if you can't truncate a series? It means you have to sum the series. I always ask the, again, Chapman is misspelled there, rhetorical question. If you have a series and you're teaching series to students, what do you tell them? Do you tell them that's the first term that's important or the last term that's important? And everybody tells them, oh, we have the nth root test, we have the ratio test. It's always about the last terms. So if it's the last terms are important, why do mathematicians, when they want to work on this subject, say, I'll only keep the first term? It's nonsense. So the whole point, as Alexander recognized with Ilya Collin, was you have to add up the whole series. So here's their famous example that I learned from Alexander. Let's do an example. You see one example, you've seen some sense, you've seen the whole flavor. So let's do a simple example. So what Alexander and Ilya did was they said, okay, Boltzmann would be a hard problem to do the computation, but let's take the grad system, which is a system of it's more than that, a system of partial differential equations, 13 moments, so 13 equations, for the conservation of mass, which was here. So it's just linearized grad. So it's a linearization. So it's taking moments of the Boltzmann and then linearizing and then doing a closure. But it gives us an idea of what's going on. So here's conservation of mass, conservation of momentum, conservation of energy, and this would be called the stress relaxation term, the heat flux relaxation term, and the pressure in the linear theory is just given by density plus temperature. It's not important. Here there's no epsilon, but we can put the epsilon in by putting back in the scale, which I'll do in the next graph. Next slide. Okay, if you put in the epsilon and write down the equations and one space dimensions, it's particularly simple. So no highfalutin stuff here. So there are the equations in one space dimension. Extremely simple problem. So I'll say it again. We've made a very crude approximation to Boltzmann in terms now of a system, of simple system of PDEs, but we can understand the Chapman-Ensgog expansion based on this very elementary level. So let's write out the Chapman-Ensgog expansion again, and the whole idea is to compute the sigma, because if we can compute the sigma, then we just have equations for P and U, which is like balance laws of mass and momentum, and we can find out what's going on. So we do the Chapman-Ensgog expansion, and it's very easy. You can write down the first few terms. The first 2-3 terms are easy. To write down the general term took Alexander and Euler. Not so easy. Okay, but the first terms, and you see this, how it goes. It goes an epsilon with a ux, an epsilon squared with a, should be a second derivative, they're typing here. So it should be a second derivative of p, then a third derivative of u, then a fourth derivative of p, and it alternates back and forth. Okay, so then the hard part, which I didn't do, which Alexander did with Euler, let's do the, okay, is to see what the truncations are doing. And the truncations are very easy to see in this case. So as a no surprise, okay, at Navier-Stokes order, if you truncate it at order epsilon, looks very good. This is the spectrum. Everything's decaying, just like the heat equation, minus kappa squared. At Burnett order, for this simple case, things are looking pretty good still. Some oscillations, but still the real part of the spectrum, negative, everything's decaying. But now we reach the moment of truth at the level epsilon cubed. We get that when k squared is big, high wave number, high frequency oscillations put into the system, the spectrum becomes positive. So it would say you have a gas, it's at rest, you solve the initial value problem, and what happens? Solutions grow. Well, that's nonsense. Can't be happening. So it shows, again, what happens when you do truncations. But as I said, Alexander and Euler said, don't truncate, add up the whole series. Well, it's rather amazing. You can add up the series and get a closed form expansion. So what does it do? It says in this kinetic problem, we can exactly change it into a PDE. So we've gone from kinetic to PDE. So you can sum the Chapman-Ensgog expansion, and the easiest way to do it, of course, is to take Fourier transform, because it's derivatives of x, second derivatives. So take transforms and work in transform space. So we take the so instead of writing down the Chapman-Ensgog expansion, which we want to find the full sum, we take the Fourier transform and find the Fourier transform of the Chapman-Ensgog expansion. So take the Fourier transform. As I said, it has powers of u, which are now written here in this transform version, and powers of p. See, it's powers, so it's k squared to the 2n, where k is the transform variable. You write them down. This sum you write as some power of some function of k times the u hat, some function of k times the p hat, where this is the formulas for capital A and capital B. Okay, very interesting observation here. Two important observations. Okay. Observation number 1 is there are two terms, the A and the B, but the A and B are not independent. So I'll go backwards in instant replay here. Notice the A here is multiplying, I can push this. I don't know. Not very good. Okay. The A is multiplying the U hat. So this is the viscous term. But here's another term entering, which I call the capillarity term. Viscous term, of course, is in Navier-Stokes. Capillarity term, not in Navier-Stokes. So I've added a new term that occurs because of the Chapman-Enskog expansion. So it's clear as we go from the kinetic theory to the PDE, we're not getting Navier-Stokes. Then you'd say, okay, I'm a PDE person. I like viscosity. I never heard of capillarity. What's this nonsense you're telling me? Let's forget about the B and just keep the A. It makes the problems parabolic, or steady state problems makes them elliptic. So who needs your nonsense? And the answer to that is you can't have one without the other. Okay. If A is 0, B is 0, and if B is 0, A is 0. So what does kinetic theory tell you? They're like twins, forever linked, and that's the way it is. Okay. Furthermore, what are A and B? How do you know what they are? And the answer is miraculously, let's go back. Okay. Not very good. The A and B, you can call C equal to K squared B. So if you know B, you know C, and C satisfies what I call the fundamental cubic. So now it's a good chance to look in the book and find out what the solution is for a cubic equation. You have the formula for a cubic equation. You can look up the solution, and you can get a graph. So now you know C. If you know C, you know B. If you know B, you know A, and you've summed the Chapman-Enskog expansion closed form solution. So you've changed closed form. This version of Boltzmann, very simple version of Boltzmann, into a PDE. Magic. Okay. What does it look like in Fourier transform land? That's the evolution equations. Okay, you can look at the spectrum. I won't bore you with that too much. So you can write down the evolution equation. So this should be the improvement of Navier-Stokes. The improvement comes from the B. Yeah. K is Fourier transform, so e to the ikx. So, and to get back to the real equations, you take the inverse Fourier transform, and that would reproduce what we would think of as the Euler equations improved upon. So this is the Fourier transform of the evolution of equations of a gas. Okay, we can check the spectrum. The main thing is the spectrum, all the spectrum, because C is wherever it is. The spectrum is all in the left half plane. Oh yeah, because C is negative. So C is negative, so the spectrum is all in the left half plane. So the anomaly of the instability occurring doesn't occur. That is the anomaly from truncation, where we'll always get an instability occurring from the truncation. If you add up all the terms, no instability, and the fluid at rest, the gas at rest, will be asymptotically stable. Okay, there's a picture of the spectrum, and that's very important. So there's a picture of the spectrum. So what does it look like? Everybody's taught undergraduate ordinary differential equations. It looks like a damped oscillator, but notice the damping is just like e to the minus t times e to the I something k omega t. So the spectrum, for the heat equation, of course, it would be going out on the real line. But here, the spectrum is going down here. That means showing its high frequency oscillations. So the oscillations are much worse than, the oscillations are much, causing you much more pain than the damping is helping you. So we see the asymptotic behavior of the spectrum. Okay. And I said one issue not addressed by Alexander and Ilya in their papers was what's the entropy equality? What's the conservation of energy? We just had in Catherine's talk an energy statement. So here's again a conservation of energy statement. And the conservation of energy statement, well, just you can write it down in terms of Fourier transforms from the equation, or you, as I said, take the inverse Fourier transform. I'll go back here and use the Plancherel formula, and there's the statement of Parseval equality, and it says, okay, that we have a energy equation. It says the derivative of the first expression plus the time derivative of the second expression equals the third right-hand side. The right-hand side is negative, so it says the time derivative of the usual energy, the little L2 norm, rather the L2 norm, plus this capillarity term, B is negative, so this term is positive, is balanced by the viscous dissipation. Okay. I put it in a statement here that Alexander was nice enough to put in the article that's going to appear. It's actually on the web in the Bulletin of the American Math Society, a survey paper by Alexander and Ilya on this subject, and they very nicely put this equation.
With reference.
With a reference? Okay. But I think it explains the whole Boltzmann and story in one sentence. It says the time derivative of the mechanical energy plus the time derivative of the capillarity energy equals the viscous dissipation. The usual theories leave out the capillarity term, and that's a mistake. Okay. Not my mistake. It's the mistake of the other theories. It's as I said, it's what you wish for as opposed to what's true. Okay, so justice is given in Korteweg's, and when did this occur? So what kind of theory produces such a balanced laws? And the answer is it was given by Korteweg himself of the KdV equation, same Korteweg, at the beginning of the 20th century. And Korteweg wrote down a fluids theory that incorporates exactly these ideas. And here it is. So here's the Korteweg's theory, and Korteweg has what I would call a higher order stress term. It's exactly as I was trying to capture, is captured in this very simple Chapman-Enskog expansion. Okay, now we get to Alexander and I were talking about this, so how do I know this is the right theory? Good question. First, I'm telling you about kinetic theory. I made up some PDE, and now I'm saying, oh, but this looks like a fluids theory. Then you might say, oh, if it's a fluids theory, could be an infinite number of fluids theories. How do you know this is the right one? And then I ask, the answer is, well, let's think about it. What did we see from Alexander and Ilya's summation? We saw that Boltzmann will lead, when you can sum the Chapman-Enskog expansion, to a second gradient theory. So second derivatives of the densities. First derivatives is Navier-Stokes, because one derivative of the velocity. Second gradient theory is two derivatives of the density. Plus, so only second derivatives can appear. And then you ask yourself, what possible theory satisfies the rules of the road of continuum mechanics? Infinite number of theories, yes, but only one will satisfy the true second gradient theory, and that's Korteweg's theory. There is no other, because you write down the most general Korteweg theory you can imagine, and that's it. So, and it's not a lot of choice, just as Navier-Stokes is the only choice at first gradient theory. Okay. So here's the energy inequality for the story. So let's stop for a second and see what does it mean. It says, let's go back to Berger's equation. So I said Berger's equation isn't telling us the truth. Okay. If we wanted to find out what the truth is about shock structure, even in this simple example, we need to have the next highest gradient with a good sign. Okay, such a case would be the KdV Berger's equation. Not surprising, Korteweg's name enters here as well. And the question would be, somehow the right question to ask about shock structure would be, if you want to think of it coming from Chapman-Enskog and Boltzmann, would be, what's the viscous limit of KdV Burgers? Much harder problem than Burgers itself. Okay, why is that? Because if the viscosity is absent, of course it's just the regular KdV equation, and we know that as epsilon goes to 0, we cannot produce weak solutions to the conservation law U sub t plus u sub x equals 0 after the shock forms. That was the work of Livermore and Lax. Okay, so it begins to look a lot like the story, and that what I was saying at the beginning. What is the state of the art for the people from the kinetic theory trying to go directly from here to there? Everything works fine until the shock forms. But if the shock is going to form over here, not so easy to go from there to there. Exactly as in KdV Burgers. So when can you pass to the limit in KdV Burgers? And the answer is, let's go back, sorry, is, okay, the viscosity term, which is an easy to see, just look at traveling wave solutions. This decay has to be sufficiently small that the viscosity term beats out the capillarity term. Okay, so you might say, okay, so when the thing you just did, you added on this higher gradient term, so probably viscosity beats capillarity, and you can pass to the limit. But I just showed you the spectrum, and the spectrum, remember the spectrum looked like this. In fact, capillarity was beating viscosity. So things were not looking so good. So we're trying to take the limit of a highly oscillatory sequence. And taking the limit of highly oscillatory sequences for nonlinear problems is a bad business. So it's no surprise that the analysts are not able to go from here to there. Now I'll need some assistance on changing the, ready. Now, while I get some help switching to then I ask the rhetorical question, because in the last 10 minutes, you might say, how do you know you're right? Well, how do we know Alexander's right? We can argue about it, we could have discussions, we could go out for a drink. But the question is, we can do better than that. We can do an experiment. So let's use analysis and experiment. Okay. So the experiment is, let's take a gas and put it in something where the effects of the Korteweg theory will tell us what the answer is. So here says you can go on the web. One simple situation is the problem of thermal creep. And the problem of thermal creep is best illustrated at a toy you can buy in a toy store, which is called the light mill. And it's more or less you have this little windmill sitting inside almost a vacuum. And I'll explain why, which is a piece of glass. You evacuate everything, and then you shine a light on it. If you shine a light on it, it begins to spin. Okay, now you might say, it's because the light sets up heats the gas, and the gas, because its pressure is temperature dependent, then it probably changes the pressure and causes a pressure. But if you think about that, if you just shine the light from all directions, then it's in perfect equilibrium, and how does it know which way to spin? So that story is bogus. Okay. Also, if you completely evacuate the gas to a perfect vacuum, and you shine the light, nothing happens. Okay. But if you put a little bit of gas, then it's rarefied, and you shine the light, and it spins. So why does it spin? Because the foil on one end is not the same, on the different sides is different. And what's causing that is the gas is moving because you set up boundary conditions on the little windmills. Okay, what we'll do is there's a whole story on the web about it. I won't go, you can read it if you want. But the problem was first investigated mathematically by Maxwell. If you can't read it, that's the Maxwell's paper in the Proceedings of the Royal Society, 1879, the year Maxwell died. Okay. And Maxwell knew about this toy and the experiments that had been done and was trying to find an answer. And Maxwell, of course, was a contemporary of Boltzmann, and he mentions Boltzmann in the article, and he says the only way to approach this problem is via the kinetic theory of gases. So Maxwell again goes through the story. He knows how to take moments. Okay, and Maxwell wrote, again, people seem to forget, wrote down the Chapman-Enskog expansion. Maxwell was doing this in 1870, he died in 1879, so let's say roughly 1878, 1877, years before Hilbert, Chapman, Enskog, and Maxwell writes down the Chapman-Enskog expansion. Okay, let's continue. It's not important. Okay, so here's Maxwell's paper. Maxwell says, the phenomenon to which Professor Osborne Reynolds has given the name thermal transpiration was discovered entirely by him. He was the first to point out that a phenomenon of this kind was a necessary consequence of the kinetic theory of gases. So Maxwell knew, as the Reynolds, that we needed to use kinetic theory. And what does Maxwell propose to do to solve the problem? Well, he'll write down some PDEs. Okay. So Maxwell writes down Chapman-Enskog expansion, truncates at Navier-Stokes Fourier. Navier-Stokes Fourier. He wants to see what's going to be the answer for the problem of Navier-Stokes Fourier. So what's a typical situation, and I have it there, is going to take a channel and put temperature equal to a constant times x as you go along the channel. Okay, there's the picture. So the simplest problem is channel flow, B half channel flow, then wedge flow, etc. You can write down a list of canonical problems. So let's do, Maxwell first starts off with Navier-Stokes Fourier. For some reason, Maxwell mentions Stokes and Fourier, never talks about Navier. Well, what can I say? Okay, but he writes down Navier-Stokes Fourier, writes down the balance laws, so the usual Navier-Stokes equations with heat conduction for a compressible gas. And what's the solution? You can solve the problem exactly. What's the solution, or a solution? The answer is the velocity equals 0 and the temperature satisfies Laplace's equation. This is true whether the fluid is incompressible or compressible, because U equals 0 is the solution either way, and the compressibility or incompressibility is irrelevant. So you can solve the equations. So Maxwell noticed that the solution to this problem, when you put a temperature gradient on the boundary and you plug in Navier-Stokes Fourier, the answer is U equals 0. What are the boundary conditions for U? Any ones, the usual ones. If it's incompressible, if it's viscous, you put no slip condition. If you don't worry about viscosity, just no flow through the boundary. Either way, the solution is the velocity equals 0. Okay, very nice. The velocity equals 0. So if you're an analyst, which Maxwell was not, he could have published a paper saying, I prove an existence of solutions to the boundary value problem. There's only one problem with that solution to the boundary value problem. It's not true. Okay, true mathematics, false physics, because that's not what happened in the laboratory. The gas moves. Okay, so here are the experiments that Maxwell refers to, and I'll try to get copies from the library while I'm here. Not so easy to find references, trace up references from the 19th century, but I'll try to do it while I'm here. So what did Maxwell do? Maxwell knew that Navier-Stokes Fourier failed as the right PDE, so he continued the Chapman-Enskog expansion, as I said, years and years before Chapman and Enskog. Okay, so he wanted to go out one more term, okay, and Maxwell goes out one more term, and then he makes the remark. He says, I have not, however, attempted to enter into the calculation. So he writes down the PDEs and says, oh, it's such a mess, I can't solve it. Okay, so I call this Maxwell's unfinished symphony. So what's the problem? So there's more people, as I've mentioned, who carried it out. So what happens if we try to carry it out? So I'll skip through this. So what's the test problem? Is this creep flow. We know going back to Maxwell's 1879 paper that Navier-Stokes has not worked. Okay, we do know that Boltzmann gives the right answer. Boltzmann works fine, it's just a mess and you need to use a computer. The Japanese began doing these calculations 30 years ago. So there's nothing wrong with Boltzmann. Boltzmann gives the right answer. It shows the fluid moves, but it doesn't tell us what the right PDE is in the intermediary stage. Okay, so this is a little complication, but let's get to it. So I try the quarter-Weg theory, because I've read Alexander's papers many times. I know that I feel that quarter-Weg should be the right theory to represent the kinetic theory. So let's try it as a test case. Navier-Stokes has definitely failed, so let's try it. Well, we plug in quarter-Weg theory. There's the quarter-Weg theory, the general form. As I said, there's only one. This is in the paper of Jim Serin and Ernie Dunn from the 1980s. Okay, and let's make a comparison, because this is an important point. So what does Maxwell do? As I said, Maxwell continued out to past Navier-Stokes to the next term. Well, what's Maxwell's next term? Even though he didn't solve the problem, if you look at Maxwell's paper, he gets the next term in the stress tensor as being Laplacian rho times some negative number. But if you do quarter-Weg theory and you go out to the next term, you get some Laplacian rho times a positive number. Why is that? Because Maxwell was taking the truncation, which destabilizes, and quarter-Weg, if I follow the work of Alexander and Euler, is adding up all the terms. Okay, well, which one is right? Well, the good thing is, okay, Maxwell, as I say here, Maxwell, just like Burnett, got the bad sign, and quarter-Weg gives the good sign. Okay, so we can solve the equations, and what do we get? Well, you can solve them. You look for self-similar solutions. That would be a longer story. You can change the PDEs to ODs. You solve the problem. You do a phase plane analysis, say, of the channel flow problem. And you want to know what the profile of the fluid flow would be. And you can write down the phase plane portrait. And if you want to know what the the profile will be, I'll get a headache. You turn your head to the left, and you'll see the following picture. And that's the standard picture. So this is the picture that you'll get from solving the quarter-Weg theory exactly. It's the picture you'll get by solving the Boltzmann equation numerically. And what picture would Maxwell have gotten? Can I use a different color? Of course, Maxwell had the wrong sign. So Maxwell would have gotten that. So Maxwell said he didn't complete the computation, and now I begin to wonder, in the privacy of our own house here, okay, maybe Maxwell did do the computation but didn't like the answer, because he knew the experiment, and then he did the computation, and he saw that the theory violated experiment. But who knows? He was a genius either way. Okay, so what does it mean? So we see both based on theory and experiment that we start with kinetic theory. We get PDEs. Those PDEs are the quarter-Weg theory, not Navier-Stokes. How do we know it's right? Right in what sense? Right in that it makes a prediction about the real world, which is consistent with experiment and consistent with numerical solutions of the Boltzmann equation. There is no exact solution to the Boltzmann equation for this problem. Boltzmann is very hard to solve, especially this is a nonlinear problem. I might add that the numerics that are done on Boltzmann to get the right picture only done for the linearized Boltzmann. So even the experts don't solve the real Boltzmann. Okay, so we're reaching the end of the story. I do some other, I think I have pictures. Everybody likes pictures. Okay, we can show flow over a wedge. And this is, let's stop with this one. So again, you put the gas in. Navier-Stokes would say, no arrows, no flow. What is Korteweg and Boltzmann say? The fluid moves very nicely over the edge of the wedge. And since edge of the wedge, number one rhymes, and it's 2 minutes to 4, it's a good place to stop. So that's the end.
Other questions or remarks?
I'm a little bit confused by, at the beginning, one of the things you wanted to do was you wanted to show that there is a kind of a limit from the kinetic equation.
Yeah.
And it should also hold in the case of the shock, right?
That's right.
That's the problem that we have at hand. How far is this program and?
Oh, that's a good. So Stefan asked, "Can I move this thing up and shut off the thing?" And I make a point. How do? Oh, can you see here? No, thanks. Because I didn't mention that. So, what if when we do numerical analysis to solve for shock? So we have a conservation system of conservation laws. So this is a system. F is an n vector. Okay. And what was the prescription given by originally von Neumann and Gelfand is how to find the right limit via viscosity. Okay. And the answer is that they proposed in this very simple version, you put in epsilon uxx. Okay. Then you may say, but you just told me that that's not what Chapman-Enskog gives. And I said, no, that's the mistake. Because if you write down, let's say, the so-called P system, U sub t plus, let's write it equals V sub x plus, let's write it minus, doesn't make any difference, and V sub t equals P U sub x. What do numerical analysts and conservation law people do? This would be V, so they might put in that one, but that's not the one they put in if you do numerical analysis. You put in this one. So this is the version of the Lax-Friedrich scheme. Okay, so what does it mean? It means, in fact, this is the right viscosity according to Gelfand, von Neumann, Lax, Friedrichs. Ironically, and it's not a hard computation to show, by a change of variables, and I did it many years ago, by a change of variables, this one begins to, under a change of variables, looks like that one. It is the Korteweg. That is, the von Neumann scheme is the Korteweg scheme. So Boltzmann is correct. Boltzmann gives us Korteweg. Korteweg gives us von Neumann Gelfand. Von Neumann Gelfand gives us the correct limiting procedure. So when you go to a PD lecture, and of course Stefan has gone to many PD lectures, but you would always hear somebody in the audience, some wise guy say, you can't put in that term. It's not physical. And the point is, no, ironically, that's the physical one. It's that one that's not physical. So okay, that's the good news. The bad news is the viscosity as it's put in here, okay, makes it highly viscous. But in reality, because of the nature of the spectrum, the true Boltzmann seems to be putting in very weak damping. That is, this term, put a constant here, this K is very big, too big, which means we're trying to take the oscillatory limit, just as Lax and Livermore were trying to take the oscillatory limit, and it can't work. So my guess at 4:02 Greenwich Mean Time today, March 5th, is that the Hilbert's sixth problem for a compressible gas cannot be done. You'll get a limit, but it will not be a solution of the Euler equations. Now I went 2 minutes over.
So if it's oscillating, then the mean of it maybe solve some equation.
Because it's a not, because if it was a linear problem, theory of distributions, no problem. If it was linear, but it's nonlinear, and nonlinear things go terribly bad with highly oscillatory limits. Any simple examples? Sine squared, kx as k goes to infinity.
So you think that there is really density oscillation in a shock? That's what you would get.
No, it's there's nothing wrong. Fluid mechanics is fluid mechanics, so we can do shock. It's the ability to go from the mathematical problem of going from Boltzmann is an idealization, Euler is an idealization, but the ability to go from one scale to the next is facing this highly oscillatory limit.
So you are saying the independence of the velocity.
It might be two independent problems in each one. Why we'd like to connect, the goal of Hilbert was to connect scales, but it might be wishful thinking.
But this would mean that the independence assumption of the velocity from space is the one which you would guess is violated in the.
Yeah. Question?
So I assume your expansions for A and B have finite radius of convergence, right?
Yeah.
So does that have any implications?
I pass. Alexander's done the expansion, so I would pass the question. It's good to have the author of the paper here. So Alexander, on the expansions for capital A and capital B, you know them globally because they're given in terms of Alexander's function C, and you know C explicitly. So there's really
But that's an analytic continuation, so it's not immediately clear to me what that means.
Yes, of course. So, therefore, this is may.
I give you the floor. I've worked enough.
Very strange thing. People, when they discuss Chapman scope, they discuss only two possibilities. Either we can truncate, or it is singular. It's absolute singular. It's just asymptotic and no convergence. We can say that sometimes it's convergent, but not an entire function, not as a whole C. It has some singularity somewhere, but not at zero. And indeed, perhaps it is the case. Of course, we demonstrated this. Of course, this example is the best. This is analytical. But of course, we can find algebraic invariant manifold for many equations. Even for entire nonlinear Boltzmann, we can write even first Newton iteration, and it works. It gives much more complex formulas, but with the same logic. If you take invariance equation, you can find algebraic invariant manifold in K space. Terrible formulas, long, but the result is qualitatively, and this saturation, what Marshall calls Rosenau saturation, because the first publication perhaps was Rosenau. And the saturation of dissipation is absolutely universal effect. It's absolutely universal effect everywhere for Boltzmann equation. That's all. Did I answer the question?
I think so. Thank you.
Okay. I can give additional. Oh, by the way, Marshall has several reprints of this huge paper just to
Of Alexander's paper, not mine.
no, you can print I can print for you your paper.
Any other questions or remarks? No? Let's thank both speakers again.